This is problem 15 on page 311, and as you can see, I've done a lot of the work here, so I'm going to talk my way through this. But the problem reads y double prime plus 4y prime plus 4y equals to 0. And as with all Laplace transform problems, we will need initial conditions in order to solve it. Those are the only kind of problems we can really solve. So we need, in this case, the initial conditions are given as y at 0 equals to 1 and y prime at 0 equals to 1. Well, before I go further here, I'd like to compare different methods. And when we get done with this, we'll work it by using homogeneous equations, that type of method, and compare them. And I think you'll find probably the Laplace transform method is more tedious. And but here's something to think about. We solve Laplace transform methods pretty much by an algebra technique, and then we have to look up a few things in tables. And now, what if you had a situation in which the situation was described by this differential equation, but the initial conditions were dynamic, they were changing, and you needed to react to those changes. So, for example, every minute or every second or so forth, you take a reading of these initial conditions and change them. Well, do you want to just keep solving differential equations? Or what if we solve the differential equation in general, and then once we have new initial conditions, it's just a matter of plugging these numbers in. So, for example, here I've taken the Laplace transform of the equation Ly double prime plus 4L y prime plus 4L of y equals to L is 0, and the Laplace transform on 0 is 0. And then I looked up what this meant. Ly double prime is s squared L minus y prime at 0 minus sy at 0. So here is Ly double prime plus 4 times Ly prime is 4 times minus 4y at 0 plus s times L. And then here's 4L equals to 0. So here I took the shortcut of just writing L to represent L of y. And normally at this point of the problem, I would plug these numbers in. But in this step I didn't. I went ahead and solved with initial conditions unresolved. And so I took these three terms, added them to the right side, and that was the numerator that you see here. And I also factored, this came over as positives, and I factored y at 0 out, and that left s plus 4. And then the remaining three terms with l's, factor the l out and divide by the polynomial, and this is where s squared plus 4s plus 4 came from, down here. So all this from here on down is algebra. And now, we could continue to work this problem with these initial conditions unresolved. And then we'll get an equation. And then all we have to do is plug in those initial conditions. And so it's a way of getting a solution where you could change these input values on the dime, on a spot, and a computer, for example, could react very quickly and resolve the equation and make adjustments. So anyway, I'm thinking, and this isn't quite the right example, but I'm thinking the early days of the space program, they had the first transistorized computer, big transistorized computer, was owned by NASA, and it took up a whole room. And I think it was built around 1957. I saw parts of this in the Smithsonian Institution about 30 years ago. Anyway, what I learned from that was that when they launched the early rockets into space, they would take telemetry readings every second. I think it was actually twice per second, 2 times per second. And those readings would be beamed back down to Cape Canaveral and would be run through this machine, this computer, and the computer would crank out their numbers, and beam back to the spaceship any adjustments. And so it's very dynamic, you know, twice per second. Here comes the data stream, and the computer reacts and sends data back up to the rocket, and that allows it to adjust its trajectory or its throttle or whatever in order to get it into the right orbit. You know, that rocket launch problem is one heck of a differential equation problem, and it can't be solved by anything we've done so far in these videos. It has to be done. It's such a big problem. It has to be done numerically through estimation techniques and so forth. But anyway, that was sort of an idea of a process that was in which the input values were constantly changing. You know, the position of the rocket, its velocity, its acceleration, and everything was changing constantly. And so their solution was, with the old computer, twice per second, let's change these inputs and recalculate a solution and send it back to the ship. So hope that made sense. That I'm sure they didn't use Laplace transforms, but that's the idea, that if you had a process where these were changing, then you would want to solve your differential equation so that all you had to do was plug in new values for your initial conditions. And so we could continue to work this Laplace transform problem that way. Well, I didn't. I went ahead and plugged the ones in at this point. So now I'll just go ahead and finish this particular problem. And we have L of y as s plus 4, this was 1, and then this was 1, plus another 1. And so that adds up to s plus 5 over, and my denominator factors as a perfect square, s plus 2 quantity squared. Well, what do we do with that? There's not a Laplace transform exactly like that in our table, but we can get there by splitting this up. And so I'm going to rewrite this as s plus 2 over s plus 2 squared plus 3 over s plus 2 squared. And you'll find that this is the way to go with this. So I took s plus 5, broke it up as s plus 2 plus 3. And this simplifies as 1 over s plus 2 plus 3 over s plus 2 squared. Okay, well, I'm going to need to do some erasing to wrap up this problem, but there's the idea. We could, if I kept these as y is 0, y prime is 0, then I could get a very similar type of algebra equation over here. It'd be a little more complicated, and then we could apply the inverse transform and solve the equation, and then we would have an equation where all we had to do was plug in initial conditions, and if those initial conditions keep changing, then it's just a matter of doing a computation. And so you can program that on a spreadsheet, for example, and just change the input values, and the spreadsheet would compute the answers. All right, well, I'm going to erase this and wrap it up. When we apply the inverse Laplacian Laplace transform, then we are solving for y of x, or the function y of x, is the inverse operator of 1 over s plus 2 plus 3 times the inverse operator applied to 1 over s plus 2 quantity squared. So we can break this up like this because the inverse operator is also a linear operator. All right, well, it's time to look up the answers. From the Laplace transform table, the Laplace transform of e to the ax is 1 over s minus a. So we're going to be able to use that here with a equals to -2, aren't we? A is -2 because s minus -2 is s plus 2. So y would equal to e to the minus 2x. And then here, again, a is -2 for this Laplace transform, and n equals to 1, because we have squared, 1 plus 1 being 2, n equals to 1. 1 factorial is simply 1. And so this works out to be plus x to the first power, and then e to the negative 2x. And then we also have the 3. I forgot the 3. So let me erase this, and then we'll write out the cleaned up answer. So we have the final form of our answer here. Y of x is going to be e to the negative 2x. I factor that out, so I left 1 plus 3x. There we go. And it's correct. So now for comparison, I'm going to work this rather quickly as a homogeneous problem, so we could kind of compare how much effort it takes to solve these. This is a homogeneous equation because with constant coefficients, second order, right side is 0. So we would use the characteristic equation, m squared plus 4n plus 4 equals to 0. Solve. And as you saw, this factors as n plus 2 quantity squared. So we have two roots, repeated roots. In that situation, the complementary solution would be c1 e to the negative 2x plus c2 x e to the negative 2x. So I said the complementary solution, but that's also the full solution to this problem because it's homogeneous. So y particular would be 0, so all we have to worry about is the complementary solution. And recall that when you have these roots, you end up with e to that power, and then when they're repeated, you have to introduce x's. And alright, well, now y at 0 is 1. I'm going to write this just a little bit differently here for the moment. Y at 0 is going to be, oh, hold on. I want to first do the first derivative. So I'm trying to make a point as I solve this, and you'll see where I'm coming from here in a minute. Y prime, we'll take these derivatives, that's minus 2 c1 e to the negative 2x, and then plus c2 e to the negative 2x, and then minus 2 c2 x e to the negative 2x. So there are the derivatives. Okay, so y at 0 is going to be c1. Great. And y prime at 0 is going to be negative 2c1 and then plus c2 plus 0 or minus 0. So we have a pretty simple system of equation here, system of equations. So if I had this dynamic system where these input values are changing, it would be a matter of plugging in the input values, the initial conditions, and solving for C1 and C2, and then plugging that into here, and then you can solve your problem. So there's this kind of build up about the Laplace transform method as being very good for these dynamic situations. Well, in this case, I think this compares quite favorably to that, and in fact, it's probably quicker. Well, anyway, let's finish up this particular problem. So C1 actually was equal to 1, and this is equal to 1, and so when I plug C1 into here, I got minus 2 plus C2 equals to 1, which makes C2 equals to 3. So now we can write out the solution to the problem. Y of x would be C1, which is 1, e to the negative 2x, plus 3, x e to the negative 2x. And I think you'll see that if we factor this out, we get the same answer as before. So, alright, well in this situation, I think my opinion is that homogeneous solution method I just did beats out the Laplace transform as as practical. So now I'm not a trained engineer and doing differential equations out in the field, applying them, and so I'm not sure you know, quite where Laplace transforms are going to be really the very best way to solve differential equations. But it's an interesting operator method nonetheless, and it's great math. And besides, it's a traditional part of this type of course. So anyway, you've now seen Laplace transforms and other methods of solving. Okay, well, I got one more problem to show you, and it's a bit rougher than this one.